Okay, shall we start? Exercise 1, right? Tutorial 8, exercise 1. So, do you remember your Taylor series? Infinite power series, right? So any infinitely derivable function in mathematics can be represented by a power series, right? Typically, it's something like, let's say you want to do it around the origin, so x equals 0. So we typically have something like fx is f0 plus f prime 0 1 factorial times x, so we can say that this is 0 factorial, right? Plus f double prime 0 2 factorial x squared plus and so on, right? So by computing those coefficients, f derived once applied to 0, f derived twice applied to 0, and so on and so forth, we derive an infinite polynomial, right? We have an infinite number of coefficients. And this is very nicely represented, would be very nicely represented as a stream, as an infinite stream in Haskell, right? So based on that, based on the fact that we have infinite streams in Haskell, right, we could create computations that would potentially deal with the exact expressions of functions with symbolic computation, right? So the first exercise is asking, knowing that e to the power of x is this expression, right? So 1 plus x squared divided by 2 factorial and so on, right? Which is e, right, exponential 0 plus exponential 0 derived divided by 1 factorial times x plus exponential derived twice applied to 0, x squared divided by 2 factorial and so on, right? So we'd like to represent this as a stream. And the stream would be this, because we don't need the x. All the information is contained in the coefficients, right? If we have coefficients, we have enough information for the full representation of the stream. We would only want the coefficients to be represented in an infinite stream. So we want to use Haskell streams, right? Expressions, recursive definitions of Haskell streams to define that stream. Would like to try? Yes. Yeah. So the window is open. So go to the folders there. Press and go to T08. No. Oh yes, that one. Good. And start a new file. Call it text document. Call it whatever. Put G1 as well, so that it's we know that it's from good form. So G1 if you want, okay. So you can edit with Notepad++, and then you can do load and in principle, we don't want to use integers, real numbers. Just leave it as an integer.
Okay.
Okay. All right, so that would be a good definition. Save.
Okay.
Then Alt tab to move to. All right. then you can say directly load, colon load, and the name of your file. No need for quotes.
So, I also keep having this error on my interpreter.
Parse error. Oh, so you're no, you don't need the let. You just say e series equals.
Okay.
All right. So now show us. Okay. Yeah, let's do something else. So that's very good. Let's go back and import data.ratio.
Import
Data, capital data,
data
dot ratio, capital ratio. So this is the module that has rational numbers, and instead of division, use the percent sign. You can just say load. And repeat commands. You can repeat without arrow. Right. So now we have an exact representation of this sequence. Very good. Okay. Thank you. Your name is?
Phil.
Okay. You may go to. You're from this group?
Yes.
So your name is again? Sorry? Your name is again?
Your last name. Okay, my first name starts with T. T-R-I-N.
Fonzocchio? No, you're not.
My first name is T-R-I-N. And the last name is T-H-E-O-E.
Can you come to this? One phone, I see. All right. Okay, good. Okay, very good. Questions about this?
Would it be easier to use a list comprehension?
How do you use a list comprehension? It's already, there is a list comprehension. Yes, come here and do your own.
this, I guess.
Oh, this should be square. Okay, fine. Yes. This should be
So
square time, right?
So the same.
But so compared to the previous one would be linear time. So
I see.
for every element you spend constant time. Whereas for this one, for every element you spend n. All of n. But okay, good point. Good point. More questions? Okay, fine. So, next one. Given a value of x, we want to compute the stream of approximations of ex. And the stream of approximations would be, of course, first element should be, so let's say we want to approximate to the power of 1, or e to the power some x, right? The first approximation should be 1. The next one should be 1 plus x. The next one should be 1 plus x squared divided by 2 factorial, right? The fourth one should be 1, so the sum of the first four terms, and so on and so forth, right? So the kth term of the approximation, the kth approximation would be the sum of the first k terms in the series. Would like to try that? Okay.
Where do I start?
Alt tab will take you to alt tab is it. Take the not just the x. Take also the series, right? So make the series an argument of the.
Oh,
Can L1? What does that do?
It kind of like folds L.
Can you do an example quickly in the command line?
Oh, okay.
So we figure out what it does. I have no idea. No, it's already.
Yeah, it takes a function of this and returns a list. Kind of like fold L.
So show me an example. So do a plus on.
Okay.
Let's say plus on 1, 2, 3, 4. Oh, I see.
Yeah.
Okay, that's a good one. Yeah, you might need brackets around it too. Alright. Okay. Oh, good.
Ah, shucks.
Take. do it for 1, so we sort of know the value of e for 1. So we should be computing the.
Oops. I think.
All right. Let's obtain real numbers because it's easier to. So so repeat the expression and do a map. So repeat the expression.
Okay.
And then at the top, at the beginning of the line, do map bracket \x arrow open bracket x double colon capital double colon and capital double. Capital D and double,
D.
right?
Oh,
so we're
okay.
converting to double. Yeah,
That's
twice.
it.
Yes. And then we probably need another dollar, I think. I'm not sure how it goes with $2. The current match expression with actual ratio integer. Oh, really? From
Rational.
From rational, but no. You have to say from rational x, and then the whole thing goes to double. Or let's try like that. See how it what? No, without the column, double column. So from rational is a function, not a type. Okay, let's see what that is. Okay, so yeah, it converges towards e. Okay, very good. Again, this is the solution that takes, I don't know, exponential time. This polynomial is not linear because x to the power of I would be logarithmic in the size of I would be logarithmic. And then you do a zip with, yeah, it's logarithmic. No, it's not logarithmic. It's n log n, right? Because this one is O of n. Okay, can we do, so this is a good solution, it's fine. Can we do something better? Can we do something that is a bit more efficient? So, we have this series, right? A0, A1, A2, A3, A4, right? What we need to compute is A0, A1x plus A0, A2x squared plus A1x plus A0, right? A3x cubed plus A2x squared plus A1 plus A0, and so on, right? So if I take this and if I write this again, right? A0, A1x plus A0, A2x squared plus A1x plus A0, and so on, right? What's the relationship between them? If I add this guy here, right, so what do I need to add? Let's see. No, so I need to add A1x x square x cube x to the fourth, right? So it's probably best to first create the stream of powers of x. So that could be created in the following way: powers of x equals 1 followed by map x times powers x, right? And I think many of you like this notation more. So let's see how we did on this one. So let's do take alright, so this is fine. Now for the string of approximations, so series value, let's say, for x. Alright, now we want to do what? Multiply the powers with the stream of approximations with the series, right? So we're going to have zip with so probably want to take a series here as well. Not series x, series and powers x. So once we have done that, we have to add it to the series, right? What do we call it? Series val. And 1 first, take 10. Do we have the correct values? No, here everything is 1 divided by. Why is that? Okay, if we map. Definitely not converging to E. All right, so what did we do? Let's see. So we have the powers, right? Powers are correct. Then if I have the series, I have A0, A1, A2, A3, A4, A5, let's say, and then I have 1x, x squared, x cubed, x to the fourth, x to the fifth. So this guy multiplies, right? So I'm going to have A0, A1x, A2x squared, A3 x cubed, A4 x to the fourth, and then oh, not series val I should put here, right? So if I go one off, right? I can have a 0. So we can use the scanl that you have just used. That's the easiest way. Let's use scanl here. Why is it plus? What's the difference between plus and without plus? Is it strict or what?
Oh, scanl doesn't. Scanl allows you to pass in an initial value, whereas scanl1 takes the initial value from the list.
I see. Okay, good enough.
After the flash to the
No, no. No, serious. Sorry. Okay. All right. So this will be more efficient because it will the time per element, per list element is constant, right? So whenever you use something like this, right, this is computed from scratch without taking advantage that we have computed x to the power I minus 1 in the previous element, right? So you have to be careful to do exactly that, because as you're computing in the powers, right, so the first power is 1, the second power is x, right? And when you're computing x squared, you should take advantage of the previous, right? So x squared is here. When you're computing x cubed, you should be taking advantage of the fact that you have computed x squared previously, right? You should not compute x cubed from scratch. So that will make the time a little bit faster. Is this clear? So the interesting aspect now is that we have an exact representation. We can go to as much precision as we want, and we don't have to decide at this point what the precision should be. The precision will be decided at the very top level, right? And then as the requirement for more values trickles down, right, this procedure, this stream will not compute more than it is needed. Never compute more than it is needed. It will compute exactly the number of values that are needed for the computation. Right? Whereas if you were in an eager, right, in a strict language, in a strict programming environment, what the temptation is not that it can't be done lazily, right? You would need more to instrument the program a little bit more. So the temptation would be what? To write a program like this that will compute a number n of elements in the stream and decide up front that you're going to compute 100, right? Because you don't have the machinery to allow by need computation. And then you're going to say it's 100. Then from the main program, you only need 30 terms, and you're over computing 60 elements of the stream just to be on the safe side, right? So that will be a waste of memory and computational effort and so on. Questions? All right, what's next? Integral of a power series. So how do we compute the integral? So let's say this is my power series, right? The integral of this guy. So some constant c plus a0x plus and so on, right? So we have to, the integral, right, should take a constant c, or maybe not the first argument. The first argument should be the series and a constant c, right, and produce this term c, a0, a1 divided by 2, a2 divided by 3, and so on, right? So this should be very easy. I'd like to try. Yes. So again, we have an exact integral. It's in no way. Of course, whenever we want to request a value, it's going to be an approximate value because we can't spread the entire thing. But for the time being, we have not removed from the stream anything. Everything is potentially there. If we want 100 decimal places, we can potentially obtain that.
Yeah, so the constant I just used 0.
No, put a constant. So add a c
Okay.
as an argument and make c the first element.
Yeah.
All right, it's important to have that. And then we don't need brackets. Okay, let's try. I can't remember the precedence, so just say reload. Just arrow up. Yeah, good. You already.
So
Arrow up. So let's integrate EX, right? With constant 1, right? So we find out what we used to know, that e to the power of x integrated is e to the power of x, right? So now it will be interesting, for instance, to integrate sine and see that we can get the cosine. If anybody remembers the series with sine, right? It's relatively easy to figure it out because a to the power ix, right? A to the power I is already square root of -1, right? A to the power ix is cos ix plus cos x plus I sin x, right? That's marvelous formula. So we can sort of work it out. But fine, let's stop here. Okay, thank you. So, very simple integration. And the next one is derivative. So, very similar. Who wants to try? Come on, somebody who hasn't answered yet. Janice?
Yeah.
Come on. No, you have to. So, say derive, and we take a series. And what do we do when we derive?
You have to bring down the power of x, and then you reduce the power of x by 1.
And then you again?
You multiply by the power of x, and then you reduce
Right.
the power of x by 1.
And you do reduce the power of x. How do you reduce the power of x?
Um,
How is the power of x encoded in our stream?
it's in a list,
It's in a list,
and
how exactly do we know? So if my series is A0, A1, A2, A3, right? Go to the PDF document. Press alternate tab, and to the PDF. Okay. So go to the previous page. Previous page. Okay, a bit higher. Right, so that's our power series, A0, A1, A2, right? Yeah. And actually we have the list of elements A0, A1, A2, and so on, right? Yeah. So how do we encode the power? What do you mean by power? In the context of a list that contains only A0, A1, A2, we don't have the x's.
Oh, you use the list composition, is it?
What do you mean list composition?
Like the third one.
Sorry, if you point on the screen, I want to see anything. Move the cursor to the right.
Like this, just that.
That's comprehension, not composition.
Oh, comprehension.
Okay, so not quite. So we use the power for us is the rank of the element in the list, right?
Yeah.
So we know that the power for A1, for instance, is x to the power of 1 because A1 is the second element in the list, right? The first would be the rank 0, would be the coefficient of x to the power of 0,
yeah.
Right? The next element would be the coefficient of x to the power of 1. The next element would be the coefficient of x to the power of 2, and so on and so forth, right? Yeah. So if you want to reduce the power of x, what do you need to do for the list?
You do zip with and then
much simpler operation. We shift all the elements to the left.
How do you do that?
How do you do that? How do you shift all the elements of a list to the left? If I have 10 people and I want to ask them to shift left by one, how do I do that? If I have a list of 10 people, a stream of 10 people, a sequence, how do you do that? When you have 10 people lined up, right? That's not a sequence. Is it a sequence of people? No. What is it? The army guys, those of you who have been in the army. You have 10 people lined up. What's that? A sequence of people? It's what? A file of people. Okay. Yeah, that's good. They have a file of people. You want to make them shift to the left. What do you do? The one who used to be the first, the one who used to be the second has to become the first, right? What do you do? You ask the first guy to move away, right?
Yeah.
So you shifted the file, the single file. So for a list, what do you do?
You take in this and then.
What do I need to do to the series? Take the tail of it, right? So if I take the tail, the second element becomes the first. Right?
But when it be the end of the series, if you're taking the tail?
If you take the tail,
yeah.
the second element becomes the first, the third becomes the second, right?
Yeah.
So the second element becomes the first means what? That whatever was the coefficient of x squared becomes the coefficient of x to the power of 1, right?
Uh-huh.
Whatever was the coefficient of x cubed becomes the coefficient of x squared.
Yeah.
So that's what we want, right? So we take the tail of the series. What do we do with the tail of the series? We have to multiply each coefficient by the power, right? So by some k. Let's see exactly which. So here we can do a list comprehension. So let's open a square bracket. So the element is going to be so let's say you're getting the A, let's call them A's, right? They're coefficients, so we call them A's. So you're getting the A from tails of series, and we multiply it by the rank of the element, right?
Yeah.
So we can say A times N bar A comes from tail series, right?
That means you have to.
Yeah, you can write like A comes from tail series. No one dot dot. One dot shouldn't be there. Right? Series as in you have an argument called series.
Okay.
Comma.
Comma inside the bracket?
No, outside of the bracket.
Okay.
Outside of inside the square bracket though.
Ah.
And N comes from one dot dot, right? Alright, that should be good. So let's see if it works. You didn't say it.
Wait. Oh.
Okay, good. Reload. And let's see. Derive E series. And then all that expression, put it inside take 10. So go at the front and say take 10. And put $1 there. Do you understand what the dollar is?
No.
Alright, instead of the dollar, put brackets around derive E series. It's the same thing.
Oh.
Okay, enter.
Okay.
Too few arguments.
So is the dollar the same as the dot?
No, it's not.
Oh.
I'll explain in a minute. Let's figure this one out.
You got C at the additional.
Oh.
Oh, why do we have a C there?
Oh, sorry.
It's okay. Reload. Up arrow, up arrow. No, up arrow, up arrow.
Oh.
Okay, up arrow. Is this correct? Doesn't look correct. Why do we have all ones? Let's go back. Let's go back. Oh, I'm sorry. No, I'm sorry. We are creating a Cartesian product. I'm sorry. We are creating a Cartesian product. We'll remove the list comprehension. Use zip width. I'm sorry.
Use what?
Zip width. So we're gonna have start deleting. I want to tell you when to stop. No.
Huh?
A bit less. There. Okay, so you can say zip width. Now you can have a star in brackets. Star. Delete. Leave the tail.
Mm-hmm.
A arrow. A left arrow. You can delete. Okay, good. the tail have another set of brackets around the tail. The brackets around the series actually are not necessary, but never mind.
Oh. So I can just remove.
We can remove those.
Okay.
And then we remove n left arrow. We remove the comma. And that's it. So let's save. Okay, now it's good. So let me explain the dollar, which can be applied in many cases. Dollar does nothing. That's the interesting thing. However, it is defined as an operator, and it has the highest precedence. Okay? So F applied to, thank you, Jens. Let me sit down. So if I say, for instance, plus 3 applied to 4, right? You get 7 as you would expect. If I say, if I put a dollar here, still get 7. There's no difference, right? Now, if I say plus 3 applied to 4 plus 5, what's going to happen now? We're going to get, right, well, actually, let's use a minus here, or let's use a star here, right? So the interesting question now is, what's the precedence of the operators, right? So what we're going to be doing is function applied to 4. So function always has the highest precedence. So function application, which is this thing, always has the highest precedence, right? And then we multiply. But what we might have intended was plus 3, and we might have intended to have brackets around here. And we were thinking that the star, we might have liked that the star binds tighter than the function application. We might have wanted the function to be applied to the product of 4 times 5, and we might have wanted the product to be 23. So then you're going to say, oh, well, no biggie. We put brackets around this, and we solve our problem. But then we have a lot of brackets, okay? So if we come with a dollar sign, the dollar sign has actually not the highest precedence, the lowest. It's an operator that binds in the with the lowest precedence. Because of that, anything on the left-hand side of the dollar and right-hand side of the dollar will have higher precedence. So you can avoid some brackets. Is this clear? So now because of the dollar, so the dollar doesn't do anything. It simply applies the left-hand side to the right-hand side. But now it says whatever is on the left-hand side of the dollar has to be fully evaluated, and then whatever is on the right-hand side of the dollar has to be fully evaluated, and only then we can apply the left-hand side to the right-hand side. So we can avoid some brackets. Right? So if we have a function with multiple arguments, for instance, plus, right? If I want to do this, so if I do this, as a matter of fact, I think I'm going to get an error, right? Because plus would be applied to 4 and star. Plus is a function that takes 2 arguments. It would be applied to 4 and star. Star is not the correct type. If I do plus and put a dollar sign here, right? This is now a correct function. You get an error message because it doesn't know how to print it, right? But it's a correct function, and I can add another dollar, and I can say here 10 minus 5, for instance, and now I should be getting
dollar closes all the way to the end of the expression, so it treats it like a bracket.
Oh, it's right associative, right? Yeah. Well, okay. So I'm not getting what I really wanted. So now I still should be using brackets like this. Okay. Okay. Not as good as I wanted it to be. All right, so in principle, you understand what's going on, right? You can save the use of some brackets. It's not an essential thing, so if you don't quite understand how it works, don't worry, just use brackets. Just remember that the function application is the tightest thing. So if you have any other expression that you want to be an argument to a function, that entire expression has to be bracketed for a correct evaluation. All right, so this is why this works. Where do we go? Here, right? So this is why this works, right? And if you find it confusing, just use brackets and you get the same result. Okay? All right, the highlight of the day is solving a differential equation, right? So you don't have to know how to solve them anymore. Did you do this kind of thing in high school? Solution to a differential equation. What's a differential equation? It's an equation between a function and its derivatives, right? So we can write the following thing: f derived x plus k fx equals c, or equals sine x. Let's make it interesting, right? So when we write this kind of thing, what's the unknown? K is a constant, of course. What's the unknown? fx, it's a function, right? It's not a value. You probably have solved equations before where you say x plus 3 equals 4, and now find x, right? So x used to be a value. Now the unknown is f, so the entire function is. And interestingly enough, this is linear. This is a linear equation because it's a constant. And these always have solutions, and the solutions are exponential. So it's some constant, some exponential, and to a coefficient. And this coefficient can be computed by a formula. You can solve differential equations of any order. So the derivative, the order of the derivative can be anything. So you can have f derived n times plus something f derived n minus 1 times plus 1 and so forth up to f derived 0 times. And the solution will be a combination of exponentials. And all the coefficients can be easily found out. Right, so there's a theory. The guy who created the theory of ordinary linear differential log equations is Gauss, who also came up with the E number. And the interesting thing about Haskell now is that, you see, we're going to just write the equation and have the system solve it for us. We don't have to know how to solve it anymore. Okay, so the system is that good with once we have infinite series. So how do we do that? So we know how to derive, right? And we know, but actually, we don't want to derive. That's one insight that we want to take into account. You see, we are given this. All right. So why is this important? Is the first constant in the power series. Why is that important? Because if fx is a solution to this equation, fx plus any c would also be a solution, right? That's a very interesting thing, right? So actually the solution is not unique. It's unique up to a family of constants. So then to single out this constant, we always have to be given an initial condition. Now, you may think of this as space, and you may think of this as, what's the derivative of space in physics? Derivative of space in physics.
if that's displacement, then that would be velocity.
Yes, velocity. Right? So this is, you can think of this as a movement equation. So I have this initial position, and I throw, let's say, an object in a gravitational field, right? And the object is going to go on a trajectory that is a parabola. And then based on these equations, right, there will be a relationship between speed and space, and actually probably acceleration. So I will have to have F double prime here, and the x here would be time, right? And I could determine the trajectory, and obviously the trajectory would be the same irrespective of the initial point and initial point, right? And even initial velocity, it will still be a parabola, right? It will be like this. But I have to say what is, so this makes sense, right? I have to say what's the initial position and what's the initial speed to have full deterministic knowledge about the trajectory of the object, right? So this would be the initial condition. I have to tell you where the object is for you to be able to compute the entire trajectory. If I don't tell you the initial position, right, you can compute the function, but you won't you won't know exactly where the object is going to be in time because I haven't given you the initial position, right? So it makes sense that we want to have this. In order to take advantage of this, because we have defined two operations, right, derive and integrate. But only the integrate has the ability to take in a constant, right? So it takes a series and a constant. So if we want to take advantage of this, we have to use integrate. So when we have an equation like this, f prime equals f, we can actually disregard the x, because in Haskell, f prime x equals fx is the same as f prime equals f, right? What we really want is to say f equals integral f plus this c, which is part of the integrate function. So then this c can become this f0 here, right? So we're going to write our equation in this format, right? F equals integrate ff, and the constant of integrate is going to be this guy. Is it clear? So we can say solution equals integrate and 0. We solved the differential equation. You don't believe me? So now we say take 10 Did we say 0? No, 1. Sorry, 1 can be 0. Okay. So this is what it is. Now, we have data ratio. So one thing we can do here is use the percent sign, and then we're going to have infinite precision. Integrate solution 1. I think what we want here is maybe 1%, 1. Why is this happening? All right, so integral b. Why integral b? If I say %1 here, oh, it won't be able to have that. So list of b's. So this is expected to be a list of integers. Why? Okay, so this won't work. We have to stick to. All right, so this is our solution. Oh, now it's suddenly. What exactly happened? Oh, because I put 1% here. That's the reason. All right, so now one thing we can do is check that it is equal to E series, right? So we can say, so take 10 series val of series, which is solution, and we can have 1.0 here. And why, if I use 1.0, Oh, I'm going to get powers of x. Why am I not getting integers? Because 1.0 is not a double. Alright, so let's make it a double. Alright, so I thought these conversions would work. So then we have to say map backslash x. All right, so now we see the real numbers, and we can sort of see that it converges towards E, right? We can take even more elements, and we can get the old expression that would get us the same values, and we can see that we get exactly the same values. So this one here, right, is exactly the same as this one here, and this one comes from solution, which is the solution to the differential equation, and this one comes from E series. So we can actually verify that the solution to the differential equation is, in fact, the exponential function. Clear? Oh, what do you mean? How does it work in Haskell?
How does it get the value of E by just magically making
how does that? Let me see how much I remember of my. So obviously, e to the power of x derived is e to the power of x, right? So we're sort of working backwards here, but the solution to the equation f prime equals f should be e to the power of x, right? So let's say you have this equation. What you do typically is you write f prime divided by f equals 1, and if you integrate this, you should get logarithm f equals x, and invert e to the power of x.
How is it that you pass in usage solution equals to integrate solution?
Right. So you're interested in a Haskell mechanism.
Yeah. Yes.
Because you start from C, right? So right. So you're giving it this C. So this C is the first element, right? So here this guy is the first element, and then so we have 1 as the first element. Then the next one is going to be zip width of the series. So the first element here is 1. So we're going to have the second element 1 divided by 1, right? Then the third element of this guy is going to be the second element from here. So the third element of this entire guy is going to be the second element from here times the second element from this list, right? So it's going to be 1 divided by 1 divided further by 2. So we have 1 divided by 1 times 2. So you can see how the factorial is coming to life, right? The fourth element here is going to be the third element of this guy times the third element in this list. So it's going to be 1. So the third element from here divided by 3. So it's going to be 1 divided by 1 times 2 times 3. And it's going to go further. Is this clear? So that's the important thing about streams. You don't have to think about the entire stream. I mean, you can think about it as the entire stream, but the computation will be done element by element, right? So essentially, if you look at this equation, you're going to have the C, which is 1, and then you're going to do zip width of series, right, times this guy. So the second element from here is going to be this guy times the first element from here. So we're going to have the list 1, 2, 3, 4, 5, right? From here, this is going to produce the second element. Not star, division. So 1 divided by 1 by 1. Okay? So once I have the second element, I can think about producing the third. So this is the third element. It's going to be this guy, division, this guy, and this is going to produce the next element. So 1 divided by 1 divided by 2. It's going to be here, right? Once I have the third element, I can think about producing the fourth element. So it's going to be this guy, division, this guy. I'm going to go here. 1 divided by 1 times 2 times 3. Okay? And you're going to go depending on how many elements you want to see, right? You're not going to compute more. Take will do exactly that number. Okay? So now, I wish, many more equations were that easy to solve, but actually that's about it. So linear differential equations would be as far as you can go. Actually, I think some partial derivatives equations would be, so whenever you can express the solution, only in terms of the past, right? So some differential equations are of such nature that the current value doesn't depend only on the past, but depends on the future as well. Especially in statistics, this happens. I mean, here it's very easy to think of fx as being time. But in statistics, for instance, you think of the x as being density of probability, for instance. So then it's not really time. So it's like on both sides of the current point, those values would influence the derivative at the current point. One example, for instance, is that definitely will not be solvable is Laplace's equation for it has a lot of applications, but one of the most interesting ones is to derive the temperature in a slab of metal, a plate of metal, right? So let's say you have this rectangular plate. Let's say you put this entire side to temperature T. Everything else is not connected to any particular temperature, and you're interested in the temperature in this point after some time, right? Looking at the two sizes, this equation is governed at equilibrium. So you can express it in time, but let's say it reaches equilibrium, right? So it evolves for a while and reaches a point where the temperatures all over the place are constant. The temperature would be second derivative of temperature d x square plus second derivative of temperature d y square equals a constant. So if you know Conway's game of life, right, actually you can discretize this, right? And the temperature in this point depends on the neighbors, on all the neighbors. And the problem is that you cannot think of it as, as going from one end to the other of the plate, and at each point solving the equation only, the current value depends only on the previous values. There's no such ordering. If such an ordering existed, then you could solve it in Haskell. So the Haskell streams are very good when the next value depends on some of the previous values, right? If the current value depends on some values that are ahead in the stream, then of course you can't do it anymore. You can't solve it anymore, right? So this kind of mathematics, a lot of it is in statistics and finance. So finance depends quite a bit of statistics. Has quite a bit of statistics, right? The way the way stocks evolve in time do not depend on the past, interestingly, but depend on people's expectation. Which means that actually they depend on the future a little bit. So you can't have a full causal relationship. But in physics, in most of physics, whenever you have to deal with time, of course, that what happens now will determine what happens in the future. It's not a case that what happens in the future will determine what happens now. So then this you in general get away with this kind of equations like this one. So you might be able to write an equation like this and have Pascal solve it for you. But these are the only cases. But anyway, as an application is interesting, and also interesting that you have infinite precision, right? Throughout this entire thing, we decide how much to compute, how much precision we want when we give up one argument to take. Never before that, right? At no point before we put an argument in take, a numeric argument, how many elements from the list we want to take, have we thought about what the precision should be. At all points, everything else potentially has infinite precision. We want 100 decimal places, we can have 100 decimal places. Okay? Okay, this is it for today. Questions? Not? Take attendance. I haven't taken down your contribution. So your name is? Mansheng, right? Why did it tell me you remember? Ashwin, not here. Wucheng? Okay. Thank you. Value? Good. Wishing. Into? Two. I thought what that would be. Jonathan is here. Phone is off your. Phone here. Answer C. Check here. Answer. Jeshun. Here. Answer. Tongan. Oh, and that's it. Okay. Thanks very much for coming. See you next time.